In the last lecture, we calculated the propagator for a simple harmonic oscillator, essentially using this discretized path integral version. With one modification, we had noticed that instead of using the actual path, if we had considered fluctuations from the classical path for quadratic Hamiltonians like the harmonic oscillator 1, we end up with a simple formula where you have the phase factor which is given by exponential of I by h cross times the classical action, that is action along the classical path, times an extra normalization factor which depended only on the two end times, and FTBTA could be calculated by a path integral of a very similar form as the one above, except for the fact that the variables that entered here all vanished at the two end points. This had the advantage that in a direct calculation you would not have to worry about linear terms in the exponent of a Gaussian integral, making the calculation a lot easier. Now today what we are going to do is we are going to demonstrate an application of the propagator formula that we had derived for the harmonic oscillator in figuring out what the eigenfunctions and eigenvalues of the harmonic oscillator are. Of course, we already know the answer to this question, the harmonic oscillator being one of the first non-trivial systems that you study, but it's good to see that the path integral formula that we get actually reproduces those results. So we start with this particular formula for the propagator that we had calculated earlier, and then make use of something called the spectral representation for the propagator. Let me first derive the spectral representation for you. Remember, by definition, the propagator kxbtb semicolon xata is actually the matrix element of the time evolution operator between the position eigenstates xb and xa. And for a time independent Hamiltonian, the time evolution operator is given by either minus IH tb minus ta by h cross. This can be rewritten by using the resolution of the identity in terms of the eigenstates of the Hamiltonian. So here the ket psi n is an eigenstate of the Hamiltonian H corresponding to eigenvalue En, and ket psi n bra psi n summed up over all n is simply the identity. I have used the abbreviation capital T for Tb minus Ta because, as we can clearly see from this formula, the result is only going to depend on Tb minus Ta in general. Of course, we have already seen this for the harmonic oscillator expression that we have on your screen right now. But in general, for any time independent Hamiltonian, the propagator will depend only on the difference Tb minus Ta, and that is something which follows trivially from time translation invariance. Now, using the fact that the Hamiltonian has psi n as an eigenstate, it's very easy to see that you can rewrite this expression as sum over all n, the overlap xb psi n, times e to the minus iEnt over h cross. That's what you get when you apply the exponential minus iht by h cross on the bra psi n from the right, followed by the overlap psi n xa. Now xb psi n is our familiar position space wave function at xb, so psi n of xb, whereas the overlap psi n xa is actually the conjugate of that. So you get psi n star xa is a minus iEnt by h cross. So this is the so-called spectral representation of the propagator. The propagator has been represented in terms of the spectrum of the Hamiltonian, its eigenstates and eigenvalues. In our case, since we know the propagator already, we have already calculated it, we can actually try to work back from there and figure out what the energy eigenvalues and the energy eigenfunctions are. But let me point out one thing clearly here. You see that the propagator can be written down as a sum of a large number, in fact typically infinite number of terms, and each of these terms split into a spatial part and a temporal part. The temporal part has to be a phase factor. It will be of the form e to the minus IEN t over h cross. And the spatial part for each term has to be essentially the wave function repeated twice, once for xb, another for xa. Of course, you have a complex conjugation for psi n xa. But since, at least in one dimension, the spatial part of the wave function can always be taken to be real, it's really psi n xb times psi n xa. Now, since our propagator has cosines and sines, it would be useful to write down expressions for cosines and sines in terms of the familiar exponential function. And then what we do is substitute these expressions for cosine omega t and sine omega t in our expression for the propagator, which we have just rewritten slightly. Now the twice I sine omega t inside the overall square root in front, that can be written down as e to the I omega t into 1 minus e to the minus twice I omega t, and so on. And plugging these in, what we are going to get is a product of this kind. Now remember, as I've just said, the propagator in the spectral representation essentially has a lot of terms. Each term has e to the minus IEN t by h cross as a temporal factor and some spatial factors which are products of the wave functions. So it will be useful to be able to separate out the spatial and temporal parts in these expressions. And for that, one of the things that we will do is we will use standard expansions. For example, the 1 minus e to the minus twice I omega t to the power minus half can be expanded in terms of the binomial distribution with fractional index minus half, as here. Then this 1 plus e to the minus I twice omega t by 1 minus e to the minus I twice omega t can also be expanded out using the 1 plus x by 1 minus x as expansion. That is the same as 1 plus 2x by 1 minus x, and 1 by 1 minus x has a familiar binomial infinite expansion of 1 plus x square and so on. So we use those expansions here and here. Now, you notice that this is a purely spatial term which you can take out, and e to the minus m omega by twice h cross xa square plus xb square. That is the one which goes with the 1 here, which has no time dependence in it. Of course, you have other time dependent terms, and so when you pull them all together, you can write the overall normalization factor root m omega by pi h cross times e to the minus m omega by twice h cross into xa square plus xb square. So that's this term here. And then you multiply it by e to the minus I omega t by 2 times this bracket. I've just kept up to twice omega here simply because it's going to get tedious to write down the whole thing soon. The rest of the exponent here, after you take out this one term here, can be written down using infinite series for the exponential in this form, and a similar infinite series will give you this as a first term for this particular exponent. Now let us collect terms together. Smallest prefactor that you get with capital T, that is the smallest phase factor involving capital T, is going to be simply e to the minus I omega t by 2, which you will get by taking 1 from each of the 3 brackets. Of course, the factor root m omega by pi h cross e to the power minus m omega by 2h cross x square plus xb square is very much there. That times e to the minus I omega t by 2 will be our very first term in the spectral representation. The next term, well, you will get e to the minus I omega t by 2 times e to the minus I omega t. That's going to be the next term. So that's root over m omega by pi h cross twice m omega by h cross xa xb times the exponential factor minus m omega by twice h cross x square plus xb square, which was always there, times e to the minus I 3 omega by 2. This is what you get when you take 1 from here one from here and this term from the third bracket. Of course, there's an overall e to the minus I omega t by 2 outside. So you get a total of e to the minus I 3 omega capital T by 2. Of course, you have higher and higher order terms, and it might be a good idea to try to figure out the next term in the expansion. Of course, that's going to be e to the minus I 5 omega t by 2, where you have to take this term with 2 ones, then this term also with 2 ones, and so on. Now, of course, this is not the end. There are other terms beyond this. But let's just compare what we have got with the spectral representation. It is easy to see that the lowest energy eigenvalue En over H cross has to be omega by 2. That clearly gives us E0, the lowest energy eigenvalue, is H cross omega by 2. Corresponding wave function has been multiplied together once for xa and once for xb to give you this prefactor in the spectral representation, which tells you that psi 0 has to be the fourth root of m omega by pi h cross times exponential minus m omega by 2 h cross x square. So when you write psi 0 xa into psi 0 xb, you are going to get this term. Of course, it's really psi 0 xa star, but psi 0 xa being real, that doesn't make a difference, as I've said before. Well, the next energy eigenvalue you can easily read off once again. E1 is going to be 3 h cross omega by 2. And once again, this prefactor is going to be the product of psi 1 xb times psi 1 star xa. And that immediately tells you that psi 1 x is going to be fourth root of m omega by pi h cross times square root of twice m omega by h cross x exponential minus m omega by 2h cross x square. It will be a nice exercise to calculate E2 and psi 2. E2, of course, is 5 by 2h cross omega. That can be seen clearly. Psi 2 will take a bit more work. Try it out. However, as you can well imagine, this term by term calculation is going to get more and more involved as we go further down the line. So it seems that this method, though correct in principle, can only be used for the lowest energy eigenvalues and eigenfunctions. However, if we make use of some known but maybe not so well known properties of the Hermite polynomials, you can actually explicitly read off the nth wave function for arbitrary n and of course the corresponding nth energy for the harmonic oscillator from the propagator expression. Let me explain how to do that next. In order to do that, we need to make use of a mathematical formula from the theory of special functions, the theory of Hermite polynomials to be exact. This formula goes under the name of Mehler's formula or Mehler's kernel, and this is the kind of generating function. It is a bit different from the kind of generating functions that you are used to, in the sense that this is a generating function not for a given polynomial, but a product of two polynomials. If you take the product of hn xi with hn eta and then multiply it by z by 2 to the power n and divide the whole thing by n factorial, Mehler's formula says that the sum of this from n going from 0 to infinity is given by the expression on the right. That's exponential of 2 xi eta z minus xi square plus eta square by z squared, whole thing divided by 1 minus z square. This whole thing is inside the exponent. And once you calculate the exponent, you divide that by square root of 1 minus z square. Now, I'm going to talk about the derivation of this formula a bit later, but let me now show how to use this to figure out the eigenfunctions and eigenvalues for the harmonic oscillator from the propagator. If you take a look at the propagator side by side, you would realize that you do have something which looks like the right hand side in the sense that you do have an exponential. You also have xa square and xb square in place of xi square and eta square. you also have an xa times xb instead of xi eta. So we are at least on the right track here. The next point that has to be remembered is xi, eta and z in Mehler's formula must be dimensionless, as is sort of obvious from the expressions. On the other hand, xa, xb are not dimensionless. So what we need to do first is change them over to dimensionless counterparts. And that's very easy to do. You just use the fact that root over m omega by h cross has dimensions of inverse length and use that to define xi as root over m omega by h cross times xa and eta as the same factor times xb. Once you do that, you plug this into the expression. The propagator now looks like the following. You have the square root of m omega by twice pi I h cross sine omega t outside. Within the exponential, you have twice xi eta, that's this term. Root over m omega by h cross whole square has been absorbed inside xi and eta with minus I by 2. The minus comes from this minus and you have an I by 2 times cosec of omega t. And you also have an additional piece, xi square plus eta square times I by 2 cot omega t. So once again, this looks like we are on the right track, almost at least. Thing within the exponent at least is beginning to look promising. 2 xi eta z by 1 minus z square. Here you have 2 xi eta into minus I by 2 cosec omega t and so on. So in order to make this expression look more like the right hand side of Mehler's formula, what we will do is we will choose z such that z by 1 minus z square, which is the coefficient of twice xi eta in Mehler's formula within the exponent, is whatever you have as a coefficient here, that is minus I by 2 cosec omega t. And from this I should be able to read off what z should be. Now that's pretty easy to figure out. You just put in the expression for sine omega t in terms of the exponentials, and once you do that and cancel out the 2's and multiply the I and minus I together 1, you can make it look exactly like z by 1 minus z square simply by multiplying both the numerator and the denominator here by e to the minus I omega t. And once you do that, it's obvious that z equal to e to the power minus I omega t will definitely fit the bill here. So, twice xi eta z by 1 minus z square, that term is very much present. What about the next term? What we want here is z square by 1 minus z square with the minus sign. But do we have that? Let's check. I by 2 cot omega t is, of course, I by 2 e to the I omega t plus e to the minus I omega t by 2, that's cos omega t. And this is 1 by sin omega t. And if you cancel out the factors, these two 2's cancel out, 1 2 remains. The two i's multiplied together gives you a minus 1. And if you multiply through by e to the minus I omega t on both the numerator and the denominator, you are going to get 1 plus e to the minus I twice omega t by 1 minus e to the minus I twice omega t. That's 1 plus z square by 1 minus z square. So we have not exactly got what we wanted. What we wanted was minus z square by 1 minus z square. But frankly, you've got something very close. You've got minus half minus z square by 1 minus z square. So there's an extra minus half. But as you will soon see, that's not really a problem. Well, you also need to worry about the sin omega t term here. This twice I sin omega t you have within the denominator of the square root in the preceding factor is simply e to the I omega t minus e to the minus I omega t. And this also comes very close to what we want in Mehler's formula. Remember, Mehler's formula has the exponential. It also is divided by square root of 1 minus z square. Here you are dividing this whole exponential by this factor, square root of 2 pi I h cross sin omega t and so on. And it's easy to see that twice I sin omega t, it actually gives you 1 minus z square. So square root does give you the right factor. But there's an extra by z here. And now let's put that all back in. So in terms of this new variable z replacing omega t, what you have is root over m omega by pi h cross, that's the factor outside, apart from the twice I sine omega t, which is here. Of course, you're taking the square root of that, divided by it. So you've got root z by 1 minus z square. Then you have the exponent that we wanted, twice xi eta z by 1 minus z square, and xi square plus eta square multiplied by minus half minus z square by 1 minus z square. So now let's isolate from this whatever we have in Mehler's formula. If you take out this factor root over m omega by pi h cross and root z, the rest of it is exactly the right hand side of Mehler's formula, apart from this extra factor of e to the minus xi square plus eta square by 2. So now we are in a position to use Mehler's formula. You just replace this whole thing by the sum in Mehler's formula. What I have done here is actually I have written the whole thing down and have also replaced z back by e to the minus I omega t. So this root z is e to the minus I omega t by 2, and this of course is z to the n. And just one more step and we are done. This is actually the sum from n going from 0 to infinity of root over m omega by pi h cross 1 by 2 to the n factorial h and xi e to the minus xi square by 2. I'm carefully splitting the xi term and the eta terms apart. You have h and eta e to the minus eta square by 2, and the e to the minus I omega t gets an n from here and a half from here, so this is what you have. Just compare this with the spectral resolution of the propagator. K has to be psi n of xb psi n star of xa times e to the minus I en t by h cross. Now comparing these two, it's obvious that en has to be, or rather en by h cross has to be n plus half omega, and the rest of it are just the two wave functions multiplied together. xb of course is there inside xi, xb is of course there inside eta, and xa is there inside xi. And in general, the nth psi of x has to be the fourth root of m omega by pi h cross into 1 by square root of 2 to the n factorial, so that multiplying the two together will give you what you have here. And hn root over m omega by h cross x exponential minus m omega by h cross x square by 2. I've just gone back from xi and eta to the corresponding variable, dimensional variable x here. As you can see, we can directly read off the energy eigenfunctions and eigenvalues for the harmonic oscillator from the propagator that we have already calculated. Of course, for that what we needed to use was Mehler's formula, which is perhaps not that well known. So in the next mathematical interlude, I am going to derive Mehler's formula for you. You can skip that particular section if you are not that interested in the mathematical integrities. Also, I will not actually show every step of the derivation because firstly, it will take a lot of time, and secondly, it will be a great idea if you were to work out the steps yourselves. In this interlude, we start from the familiar Rodrigues formula for the nth Hermite polynomial. H and x is basically the nth derivative of e to the minus x square multiplied by e to the plus x square and with an overall factor of minus 1 to the power n. And it is straightforward to verify that this will give you h0x is 1, h1x is 2x, and so on. Now, in order to derive Mehler's formula, what we will do is we will write down this formula for h and x, the formula which involves nth derivatives, in terms of an integral. And the process to do that would be to start with e to the minus t square plus twice I xt's integral from minus infinity to plus infinity. And it's a pretty straightforward integral to do. You could use your standard results from Gaussian integrals, or you could just complete the square here, and you will find that the answer is root over pi into e to the power minus x square. Or in other words, e to the minus x square is simply 1 over root pi times the integral over the entire real line from minus infinity to plus infinity of the complex function e to the minus t square plus twice I xt with respect to t. Now the reason why this is useful is that In the Rodriguez formula, the principal calculation is figuring out the nth derivative of this quantity e to the minus x square. Now, if you take the nth derivative here, it's pretty easy to see that taking the derivative of the exponent will bring in a factor of twice it for every derivative. So, for the n derivatives, you have an extra factor of twice it to the power n inside the integrand. And that tells you that h and x can be written down as an integral in the following form. 2 to the n minus I to the power n, that's the minus 1 to the n in the prefactor coupled with the I to the n that you have from the derivatives, times e to the power x square by square root of pi, and followed by an integral over the entire real line of t to the n e to the minus t square plus twice it x. So this is h and x in the integral form. Just to quickly illustrate the utility of this particular expression, let me give you a derivation of a result that you all know, the generating function for h and x, the Hermite polynomial. For this, all you do is multiply both sides of this expression by z to the n, divide by n factorial, and then sum up over all n from 0 to infinity. But if you do that, the n dependence on the right hand side essentially becomes 2 to the n minus I to the n into t to the n divided by n factorial, and when you sum that up over n from 0 to infinity, what you get is e to the minus twice itz. So basically the integral on the right now has this integrand e to the minus t square plus twice itx minus twice itz. Again an integral which can be easily calculated, essentially the same integral as the one we have done before, except that x has been replaced by x minus z. So e to the x square by root pi, the prefactor, gets multiplied by the value of the integral, which is square root of pi times e to the minus x minus z whole square. And simple cancellation tells you that this is e to the twice xz minus z square, the familiar generating function for the Hermite polynomial. As you all know, various properties of the Hermite polynomials, including their recursion relations and their orthonormality conditions and so on, can be derived from this particular generating function. After this warm-up calculation, let's turn to what we really want to prove, that is Mehler's formula. There you have h and x, h and y, z to the n by 2 to the n factorial summed up over all n from 0 to infinity. So what we will do is write h and x in the form of this integral here. We will change the dummy index of integration from t to, let's say, u, multiplied by h and y, where again I will change the dummy index to something else, let's say v, and multiply the whole things together. And what you end up with is the following. E to the x square plus y square comes out outside the sum because that doesn't depend on the n. The square root of pi whole square gives you a pi. The n dependent part, which is inside, has minus 1 to the n from the 2 minus I to the n's multiplied together. You had 2 to the power n's from h and x and h and y respectively, but one of them have been cancelled by the 2 to the n in the denominator, so you get 2z to the power n by n factorial, which is of course the n factorial on the left hand side here, followed by the two integrals that you have to do, e to the minus u square plus twice I ux u to the power n du. That will give you h and x essentially, apart from those factors which we have already taken out. And the next one will give you h and y. Now, you should be pretty sure of what to do next, basically because the minus 1 to the n, 2 to the n, u to the n, v to the n, I have forgotten to write, and the z to the n together. When you sum up over all n going from 0 to infinity, will actually give you e to the minus twice u vz. So this is the integral that you have to do now over u and v. Now each of these integrals are standard Gaussian integrals, 1 over u, 1 over v. So you could use say the techniques that we learned earlier using matrices and their determinants, but in this case it's pretty straightforward. You can just integrate over v first, keeping u constant, and then integrate over u. And if you do that, I'm skipping the steps in between, but if you ultimately calculate the integral, this is what you're going to get. So I am going to not discuss all the intermediate steps. What you should be able to do is fill in the blanks yourself very easily. So this is essentially how you derive Mehler's formula. Now, as I had stated before, starting off this particular section, on the derivation of Mehler's formula, I had meant this to be a mathematical interlude between two physics applications. But I find that this lecture has already become long enough, so maybe I will draw a line here for today. In the next lecture, what I am going to do is derive the harmonic oscillator propagator once again using a different method. This will be a method which involves treating the fluctuating paths around the classical one in terms of their Fourier components. But that does not mean that we will be done with the harmonic oscillator then. We will continue with the harmonic oscillator for a few more lectures. We will discuss coherent state quantization and coherent state path integrals after this. We will also talk about a general quadratic Hamiltonian, even time-dependent ones, and see how the path integral formalism takes care of that. We will go on to talk about Fermionic harmonic oscillators, and so on. But all that is for later. Let's say bye for today.